All right, welcome to this segment on operating models, which is a continuation of our course on power system models. The objectives from this segment is that at the conclusion, you'll be able to describe the applications of operating models, how those models support the IRO, or Interconnection Reliability Operations and Coordination Standards. We'll cover the history of how operating models evolved, so you'll be able to describe that evolution. And then we'll discuss the structure of the operating models using the same UML diagrams that we covered earlier in the planning segment. We'll then describe the actual operating models for key power system components, generators, transmission lines, transformers, and so on. Then we'll also discuss the evolution of the NERC reliability coordinators. These are the entities that have the responsibility for the IRO standards and the high-level responsibility for ensuring that the system is reliable, and then they direct the transmission operators and balancing authorities to follow the correct operating procedures to maintain that system level reliability. And then at the conclusion, we'll discover the pros and cons of operating models versus planning models. So let's get started on the applications for operating models. So if we look at the applications of operating models, one of them is for operations planning from 1 week to a season ahead. And if this slide looks familiar to the one that we had with planning programs and planning models, you're exactly right. Really, we can have either planning programs used to manually recreate operating conditions, or we can have operating models automatically updated. So clearly, if a utility has made the investment to bring in the real-time data, to calibrate that data with State Estimator, and get the real-time sequence running, the operating models are a much better way to do the operations planning. This way, there's typically still an operations engineer, and that engineer's job is to run these studies a day ahead or a week ahead. And so the level of manual intervention is much less. Literally, they can take, with a single push of a button, they can say, I want to retrieve this historical condition, or they can take a real-time snapshot, and then basically they can start making changes to that. So they're not having to go through and manually take lines out of service, adjust generation levels, adjust load levels. They can really just take a historical snapshot or the current condition. So again, those models can be used to look at different contingencies, develop preventative action plans for those contingencies, and develop remedial action plans to how the operator should respond after that event occurs. They can be used to update transfer limits. And they can provide an excellent case to train operators in identifying the worst contingencies and training the operators in what to expect. You don't have this big gap between the types of tools that the engineer is using for planning and the different names. We talked about all the bus numbering being different. In this case, everything that the programs are using are like a mimic of the real SCADA screens. And so you're just seeing study results on very similar screens to what you're seeing for the real-time results. So this is a much more natural environment for the system operators to also work with. We talked about the operation engineer typically works 8 hours a day, 5 days a week. And so if the operations engineer is not available, then the system operators themselves can run their own studies and can be looking at the different conditions which may have occurred that the operations engineer did not happen to study. So again, we're really, these programs work very well, but there is a higher level of maintenance to get them because you're running from real-time conditions, there may be an error that happens from the real-time system. Maybe a breaker is telemetred incorrectly, the State Estimator diverges, so you do have to have that additional model tuning and effort to keep the programs running. And again, for real-time operations, this is the same set of applications we talked about for planning programs, but operating models with the breakers and switches and being calibrated with the real-time measurements is a much better solution. So I can summarize to say that in general, all the reliability coordinators have operating models and a real-time sequence of network applications, and some of the larger transmission operators have that, but we still see a lot of the smaller transmission operators not having these applications online and running. So for real-time operations, we're looking at hour ahead, we're looking at current conditions, and again, we're looking at contingencies and updating the preventative action and remedial action plans. And of course, if there's a request for an outage that may be due to an emergency requirement, maybe there's been a broken insulator, or a conductor has come loose from the insulator stack, and it's really important to get that line out of service to repair it, then these programs can be used to very quickly run the impact of that outage and see how the system may have to be rescheduled so that that line can safely come out of service and not jeopardize both the real-time conditions as well as the contingency conditions. So in the next segment, what we'll do is we'll cover how operating models support the IRO standards. This is a very comprehensive set of NERC standards for interconnection, reliability, operations, and coordinations. If you're working for a reliability coordinator, this is the primary set of standards which govern how you will act. If you're working for a transmission operator or a balancing authority, then you will be reporting to a reliability coordinator, and you will be supporting that reliability coordinator to maintain compliance with these standards. Let's review a recap the key definitions of system operating limit and interconnection reliability operating limit. We did cover this in the transmission network flows course, but these are really fundamental. And so we do this with the concept diagram, and what we can look at this diagram and say there's really two key parts to it. There are the facility ratings and the operating criteria. So facility ratings is primarily determined by thermal constraints. How much current can that conductor handle if it's a transmission line? How much current can that winding of a transformer handle, or say the field winding or the rotor winding of a generator? So if you exceed the current rating, the temperature will get too high, you'll cause damage to insulation, and there can be a fault. And then we have system voltage limits. That's basically the maximum and lower limit for the voltage on equipment and bus bars. If you go too high, you have a risk of flashover and damage. If you go too low, then you've got the issue of the custom equipment is running at low voltage, or that can be an indication of a voltage stability limit. Facility ratings and voltage limits, you can monitor those just by looking at your actual measurements and comparing them to the limits. But transient stability limits and voltage stability limits, you really have to run a simulation, because you're conjecturing for transient stability limits that a fault has occurred on the system. Through that simulation, does the system stay in sync, or does it go unstable? For voltage stability limits, again, you're taking lines out of service, and you're looking at, as you move more and more power across that transfer, where do you get to the knee of the curve, which we talked about, and you go into the voltage collapse. So really, simulation and models are at the heart of these types of limits for both the transient and the voltage stability. But now look at this in a little more depth. It says for both pre-contingency, which is the state of the system right now, or post-contingency, which is after an event has happened. So really, there's no way you can look at what will happen on a complex power system without running a detailed simulation with a model. So in the post-contingent state, all of these ratings have to have models which the operator can run and determine, is the system running within the operating criteria. On the other side, we're monitoring the real-time conditions. We have the flows, the megawatt, the megavars, the amps, the frequency, and the volts right throughout the system. And so the job of the reliability coordinator and the transmission operator, all as a team, is to make sure that you're very well aware of your limits and you're monitoring your real-time conditions to make sure that you're staying within the most limiting operating criteria. It's understanding that the flow on an interface can actually be governed by a number of different criteria. You as an operator have to understand which is the most limiting one. It can be the actual thermal rating, a stability rating, a voltage stability rating, or it can be a voltage limit. And again, we say it over and over, it's got to be for your pre-contingencies as well as all your N-1 contingencies and certain multiple contingencies. And that basically sums the job up of maintaining the system so that we do not have the cascading blackouts. Now, all of those system operating limits, literally, there can be one for every transmission line. There can be major paths that you have to monitor, as well as the bus bars, the generators, and so on. But out of all of those limits, we have a very special subset, and that is called the Interconnection Reliability Operating Limit, the IROL. And that is that set of system operating limits that will lead to instability, uncontrolled separation, or cascading outages, which will, of course, affect the reliability of the bulk electric system and can leave millions or tens of millions of customers in the dark. That's the goal, is to find the, and normally those limits will be identified for you ahead of time by your engineering staff. But if for some reason the system gets into a very unusual condition, you may have to actually figure out for yourself which of those interconnection operating limits and take some action to alert your reliability coordinator. And like we saw in the September outage in Arizona and California, any one of the system operators at different levels could have actually run some studies that said when that Gila to Hassayampa line goes out of service, we have a instability and a cascading outage. So we've talked about then the reliability coordinator responsibility and authorities. And this is the IRL 001 standard. Basically, the reliability coordinator shall have the authority to act and direct others to prevent events that cause an emergency. The others, the transmission operators, balancing authorities, generator operators, distribution providers, will comply with the reliability coordinator directions unless basically we have a safety violation, lives are in danger, we have potential damage to equipment, or there's some regulatory law or statutory requirement is being broken. For some reason, maybe you've been asked to redispatch generation, but that is going to cause an environmental violation of emissions or maybe too much hot water going out into the cooling system. And so the entities, the transmission operators, balancing authority, generator operator, distribution provider, shall of course always inform the reliability coordinator if for some reason it doesn't have the ability to perform that task. The next standard, 002, covers all the facilities. Here's an example of the control room for the Midwest ISO with their overall situational awareness shown by the extreme large system diagrams and with different operators monitoring different parts of the system, as well as a desk for the overall supervisor, and then there will be desks for the actual operations engineers. And in this particular case, they run the market in addition to running the reliability function, so there will be marketing desks there as well. But basically, from the reliability point of view, they shall have real-time monitoring of their own area as well as their neighboring areas. It's very important. On a large interconnection, we can have the Midwest ISO are connected in with PJM. It's important that they be able to jointly share studies where an outage in one region may have an impact on another. So they will identify the SOLs and IRLs with alarms. So there will be messages coming to the operators when there are violations. They will monitor all their bulk electric system elements that could result in SOL and IRL violations, including generators, lines, buses, transformers. They'll ensure that those elements have measurements. And then they will have analysis tools, state estimation, contingency analysis, wide area displays to monitor the thermal, stability, and voltage limits. So this is saying, really, the reliability coordinator has to have operating models. It has to run these applications in real time. It says they will control the maintenance outages. When those outages are taken out for service, then they have to make sure that it's either at a non-critical time or they have a backup for that. So it's saying that these tools have to be a critical function. And again, we talked about just one data entry error. Getting the reactants out by a factor of 10 can be enough to cause those programs to diverge. So it's really important that those models be accurately calibrated and tested so that we have reliable results. The real-time network applications, which we'll actually get into more detail in the next course, include the topology processor, which is determining which buses are electrically connected, what lines and equipment is in and out of service. The state estimator, which is coming up with a best fit. It's basically looking for bad data, and it's providing, if you have a part of your system which is not measured, it can provide calculations. There's an external model. We talked about modeling your external system. The bus load forecast is looking at when you're doing your operations study. It's nice to say, well, the buses at 10 o'clock tomorrow are basically going to be at all these values, so you actually can forecast the individual loads on buses, not just your system load. You have your contingency analysis, running all the different outages, telling you what's overloaded. Your dispatcher power flow is where you as the operator can make your own custom studies to set up the system in a different configuration. The optimal power flow can help you. It will actually give you recommendations about how to redispatch the system to keep things within limits and also minimize production costs. And then the operator training simulator, of course, is what you use as part of the exercises, is another really good application that ideally can build on the same models that are supporting these applications here. So those are the applications that are a normal part of a reliability coordinator. Another aspect, and especially that came out of the 2003 Northeast blackout, which took out 60 million people over many different states in the Northeast, is that the reliability coordinator has to see the big picture. They have to bring in data from their neighboring organizations, and they need to have displays so that they can see what is happening on a global scale. So this standard says they'll monitor all the bulk electric systems of facilities with their own and adjacent areas, again, to determine potential SOL and IRL violations, and regardless of whether it's a planned or unplanned event. They will include critical subtransmission facilities, and they will know the status of facilities that where the degradation or disconnection could result in the SOL IRL violations. This standard, 004, is highlighting the operations planning that the reliability coordinator will conduct for its area a next day reliability analysis to ensure that it can be reliably operated in both anticipated, normal, and emergency conditions. Those studies will highlight interface and other operating limits, including overloaded lines, transformer voltage stability limits. And they will build plans to alleviate those violations. And again, this one also covers current day operations. And it says that the transmission operators, balancing authorities, transmission service providers will comply with the directives of the reliability coordinator based upon their next day assessments in the same manner as if you had a real-time operating event. So the idea is that the reliability coordinator has done this study for the next day, and they're saying that if this outage occurs, then we may have these sorts of overloads, and these entities have to treat that as if there was with just as much seriousness as if there was a real-time overload on their system. And that can be somewhat difficult to do, because that may mean they have to start up gas turbines locally closer to the load, and that's going to cost more money. So it's literally a case we're saying, in the event that this happens, this is what was happened basically with the Southwest outage, is that the organization there should have been running more expensive generation in the event that some contingency happens. And so again, it's that discipline of being willing to say, look, we're going to run our system so that in the event that any single contingency happens, we will be secure, we won't have a cascading outage. So there's a whole process of taking those violations really seriously and being willing to spend the money to run the more local, more expensive generation usually to be secure. If you don't do that, we really have the consequences are evident. We saw this with the 2003 Northeast outage, the Southwest outage. So really, it's an educational process to make sure that all the entities take those violations really seriously. But the standard here is very clear about it. The reliability coordinator will notify the impacted transmission operators and balance authorities when the results indicate adverse impacts on reliability. And then the reliability coordinator that identifies the actual or anticipated condition will notify the transmission operators and balancing authorities when the problem's been mitigated. So clearly, after the problem goes away and the transmission operator balancing authority can start shutting down the expensive gas turbines and bringing on the more economic remote generation, they need to know about it, and so that's what this standard here covers. All right, now we get into the real-time assessments. And the purpose is to prevent the instability, uncontrolled separation, cascading outages that will impact the interconnection. For those of you who are preparing to take the NERC certification test, these diagrams are really good to pay attention to. These are the sorts of questions that you will have. And we believe that these diagrams are a lot easier to read compared to all the text in the standards. So it's very worthwhile going through these diagrams to get a picture of really what is happening between the reliability coordinator and the transmission operator. And again, if you're sitting that test for the reliability coordinator, the questions are going to be directed to you as if you are the reliability coordinator. What role would you play and what decisions would you make? If you're sitting the test from a transmission operator, then the questions will be directed about how will you respond to a request from a reliability coordinator, and what would you do? And how would you inform the reliability coordinator if you found some violations? But again, from the RC point of view, they will perform the operations analysis for the next day and will exceed the IROLs during anticipated normal and contingency events. And this one is somewhat redundant with the earlier standard, but the main new one here is that they'll perform a real-time assessment at least once every 30 minutes of the wide area, and is it exceeding or expected to exceed the IROLs. And so this one really means you've got to run all those contingencies. You may be running thousands of contingencies. You may have massive parallel computers where you've got hundreds of computers all running different contingencies to make sure you can get it done within that 30-minute period. And then those programs have to boil the results down to summarize the key ones that cause the violations, so you can give that your attention. And so when the RC determines that the operations planning or real-time assessment has a need for operating actions to prevent exceeding an IROL, it shall share the results for those members to take actions. This can be having a common set of displays, but typically this is phone conversations where the RC is calling you and saying, look, Joe, you've got a violation. You need to take some action on that. So I think you can see from this the importance of having those operational models calibrated, because more and more, well, at the heart of the reliability coordinator function, there are simulations. We're seeing a lot of jobs open up, as in the WEX system. They'll be opening up a new reliability coordinator office. We've had some of our Power for Vets graduates placed there. We're very proud to say. And since the main job is really running applications and looking at the overall stability of the system, those jobs are opening up for candidates that haven't necessarily had a long history of dealing with substations, and because you're not on the end of the phone having to direct a system operator in a substation to do switching. That is done at the transmission operator level. The reliability coordinator, you're really just running studies with these computer programs. And so those types of jobs are opening up for those that have a good, in some case, an engineering background or a good analytical background, and are getting their certification. So I encourage you to follow the positions that are opening up at various reliability coordinators. It's a very exciting job. You're responsible for the lives and the reliable supply of power to literally millions of customers. And so this, anything we can do here to help you, obviously, we're very, very motivated to do that. So we've covered the responsibility of reliability coordinators from a NERC standards point of view. What we'll do next is we'll cover the evolution of operating models, and then we'll actually cover the evolution of reliability coordinator functions themselves. This chart here shows where the operating models that are used by a number of the major vendors today, Alstom, Siemens, the EPRI OTS, started out with some work at Systems Control that were then purchased by ABB, and that was performed in the 1976 timeframe. Systems Control were working out of Palo Alto, California as a subcontractor, and Control Data, who became Siemens, was the prime contractor for projects we talked about in our grid introduction program called Wisconsin Electric, Florida Power and Light, Delmarva, and they were the first major energy management systems using the Control Data cyber computers that ran all these applications we talked about on top of the basic SCADA AGC. And so that work there became a foundation for a number of spin-offs. In '79, a group of us started a company called ESCA, which became Alstom, and that started its own development of energy management applications using the VAX computer. In 1988, EPRI started a project with Control Data as the prime, and they built the operator training simulator. This essentially is the same software at the heart of the power simulator which you're doing your exercises with. And so with EPRI taking that software, it made that software available for other organizations like Inksys to license. But then another interesting trend happened is that David Nuttall left Alstom in 1990, and he started a company called Unified Information and built the Unified Database. And then when as part of this EPRI effort here, the operator training simulator manual with all its detailed models was available. So Dave was able to take that manual and build what became the Common Information Model. So you can kind of see the trace of the technology starting from this early work at ABB or Systems Control being used to, that work essentially became the genesis for all of the Siemens systems. It was the genesis for all of the Alstom or ESCA systems, and through here, the technology went from SCI to Control Data or Siemens to EPRI to Unified Information, and became the Common Information Model, which is now a standard. So that gives you a summary of the different organizations and how they were involved. So the formation of ESCA in '79 was a really exciting time. There were 12 of us that were in the Silicon Valley area. This was even before it was known as Silicon Valley. And basically, we got together and sold our houses and raised close to $750,000 and headed up north to Bellevue and started this company called ESCA, which stands for Energy System Computer Applications. The key part of that was a product called Habitat, an environment for hierarchical databases. This was before Oracle was even formed and existed, so literally they had to build their own database. And the idea is that there was a separate MOM database for the SCADA, the generation, the network, and the dispatcher training simulator. And the key people behind that were Norris Peterson, that was the project manager. Jay was the visionary to build this, and Phil Heisted was the programmer that made it all work. So it was a very exciting time. And as we all know, the Alstom systems are very prevalent, and that was some of the key people behind that. Now, the EPRI operated training simulator, that was built in the late 90s when EPRI funded Control Data. But the engine was built by Professor Bose at Arizona State University. And Professor Bose has been a very great colleague and supporter. And so as a result of that, that engine, that Fortran code, was interfaced to a database provided by Siemens. And all the documentation for this is actually in an EPRI manual called the Network Description File, and that published that information and made it available. And the program itself was licensed by Inksys in 1991, and we've continued to work with EPRI and Power Data to make that same engine more flexible and easy to use and available on PCs and Linux and over the web. So that gives you a little idea of the history of the technology that went into the actual software that you'll be using for your online simulation studies. So again, this was showing you how that basically sequence of operations led to the EPRI OTS and the engine that you're using. So let's look at the structure of operating models. You remember we talked about how the electrical bus bar is really the key for planning models. But operating models, things get a lot more complicated. We have different entities with roles and ownership and responsibility. We have to deal with the actual breakers and switches. We have real-time measurements. We have schedules for regulating values over time. We have load forecasts. And we have these different subsystems of generation, transmission, distribution systems, and the supervisory control. All these thousands of measurements that are being scanned in that have to also be displayed and manipulated. And now more and more we're seeing geographic information systems. Customers want to see their system maps on top of a GIS basis. So this is the UML diagram for the operated training simulator. Basically, the heart of the diagram is things are grouped into substations. In the planning models, they don't even really think about substations. But from an operator point of view, you're always thinking of that substation is a ring-fenced set of equipment, and you've got everything inside of that, and that's where you're directing your switching operators to go. You've got to make sure they're at the right substation. You've got to make sure they're at the right set of equipment. So those are very important. And so we have a much more complex set of grouping. Remember, in the planning model, we had a bus, and everything just connected to the bus. In this case, you really have to have a pretty sophisticated database management system that is tracking not only the equipment, but how everything is connected together. So we have zones. Every zone can have a load forecast, and the station is within a zone. And within that station, you can have different voltage levels. Your equipment is definitely at one voltage level or another in terms of the nominal voltage. And so they take advantage of that. So this is like a hierarchy of ownership. Company owns zones, zones own stations, or companies have zones, zones have stations, stations have voltage levels, and voltage levels have various types of equipment. So in the early mid-70s and 80s, a whole approach of using a hierarchical database to manage this was conceived and implemented. These nodes are what we call connectivity nodes. We'll get into how they are really critical and how they are used to define how everything connects together. So what was very popular out of this from both the systems control and Siemens, and you'll still hear this in some of the systems, is the area group table item database. That you could have a certain area. Within that area there was a group of, so you would have, say, your companies, and then within that you could have your zones and your stations, your voltage levels, and your equipment. So the whole process of coding this up was very much along the idea that there was a hierarchy of ownership. And there could be a uniqueness. In other words, your equipment, as long as it was uniquely defined within this voltage level, basically it was like you inherit all the names of your parents. So then that by inheriting the names of your parents, you have a unique name overall. So let's look at how the connectivity is defined. They have a concept called connectivity nodes or junctions, and this is where various pieces of power system equipment come together. And again, and so we see these these little squares. The big red squares are the circuit breakers. The small squares are where things connect together. So things can connect together through a bus section like this, or through if we don't have a bus section, we introduce a connectivity node or a junction, and we have to uniquely give those names. And so we would say that breaker 11 has connections, a from node and a to node. So breaker 11 goes from connectivity node 211 to 221. These numbers are put together typically by an application engineer when they're building a model. These numbers are never visible to the system operators. And so in the early days we had to build these models with a network list. We didn't have nice drag and drop tools where you could literally drag and drop and make the connection graphically. And so these systems were very laborious to build with these models, and they were error prone. You could literally say have a typo, and instead of this being 222, if that was 227, that breaker would be wrong in the database. And this can be very frustrating because when you have that sort of error, what happens is the operator would open this breaker, they would open this breaker, they would expect the flows to go to 0, and they wouldn't go to 0. Literally you had a latent error behind the scenes that might only be discovered when the operator is actually using the tool or using the simulator. Even worse, it could show up equipment that could be actually energized, could show de-energized, and vice versa. So this network list approach was very prone to error, and it became a limiting factor in terms of how large companies would build these models. In the early days, we literally have the customers would edit the network description file. This file is still generated with the EPRI-OTS, but it's all done behind the scenes, okay? But here, for example, if you've run the Palco system, you've operated the ELS station, one of the very simplest stations. Behind the scenes, the EPRI-OTS has a network description file, and again, it's hierarchical. So we have the station ELS, we have the voltage level at 230, and then we have these nodes, 1, 2, 3, 4. Here's the nodes here, 1, 2, 3, and 4. And we define the connectivity for breaker 1 as going from node 2 to node 3. We see here, breaker 1 is going from node 2 to node 3. So you see, even for this really simple substation, the amount of painstaking detail to get the right numbers in the right slots. And so this is why we saw a lot of resistance to people investing the time and effort with the engineers to do this, to build these models. Only the largest utilities that could devote several engineers to maintaining these models could afford to keep these applications running. Following through this, we see that we have loads, we have feeders, and then we have our transmission lines. That this line here is going from Ells. It's in the Ells station. We have a line going to Doyle. We see that. From Ells, we have a line to Doyle. The name of the line is Ells to Doyle, and this will be the node it's going from to. Yeah, it's going from the 2 node, and it will be going to the 8 node at the other side on the Ells station. So that just gives you an idea of the amount of detail. And so literally, this is a special type of effort to get these applications running in the past. But now we have much more sophisticated methods where you literally can just drag and drop and connect equipment together, and you don't have the problem of latent errors in the database. All right, we've talked about connectivity. Let's look at the actual equipment operating models. We talked about the need to have actual circuit breakers which can clear faults and open close under load. So the circuit breakers are the larger squares. We have the disconnect switches. Here we see a disconnect switch and another one here. They cannot open and close under load, and we can have also and they cannot clear faults. We can have circuit switches which can open and close under load, but they do not clear faults. And then it's important to know, can the operator control that under supervisory control manually, or does he have to send out an operator to walk up to the switch and crank it open? We have line data. The line data is very similar to what we talked about for the planning models. Basically a pi equivalent for a transmission line. Not too much difference there. The generating unit data is quite a lot more complicated. Instead of just having in operations, we have to say that a generator model has a synchronous machine. That synchronous machine can have heat rate curves that determine its efficiency for where it's dispatched. We talked about the megavar capability curve to determine how much megavars it can produce and absorb depending upon the real power output. And it can have 1 or 2 synchronizing breakers. These are the breakers that will actually synchronize that system. So we do see some more detail there. Transformers, we have the discrete versus continuous taps. We have the time response of the tap regulators. That transformer tap will control a voltage, but it's going to take maybe 10 seconds before it makes the first move. After it makes that first move, it may take 5 seconds before it keeps on moving that tap up until that voltage gets to the desired range. And of course, we have to designate, and we cover this under the voltage class, is that tap just fixed, or is it something that does adjust under load? Otherwise, the electrical characteristics are very similar for the planning models. We need the load data. We're running simulations, or we're looking at studies that can go for throughout the whole day, the whole shift, or even a week at a time. So we have the daily load curve, which may be different based upon the day type or the season. We assign, we have a daily load curve for the different zones. So a very large utility may have different weather patterns in different zones with different daily load curves. We have a voltage dependence. We talked about the load being divided into constant impedance, constant current, or constant power components. It's important to define that. We have the frequency dependence. When we lose the generator, the frequency drops, the load actually drops as well. We can assign those loads to different groups. It's very common that each substation has a load group, and that determines the megavar to megawatt ratio in that group. We can have non-conforming loads. Some loads, like a factory or a drag line or an arc furnace, won't follow the normal daily load curve. So a non-conforming component, that load is big enough and its characteristic is so different that you actually have to give it its own particular schedule. And then we have the cold load pickup, is that when we're going through a system, when there's a system shutdown, the load is de-energized. What happens over time is that you lose the diversity. Let's say it's a hot summer day a whole subdivision is blacked out, what's happening to the temperature of all those homes, the temperature is rising, isn't it? So let's say you're blacked out on a hot summer day for 2 hours. When that power comes back on, the load is going to come on at a much higher level because all of those thermostats, the temperature's gotten up to 90 degrees, and all of those air conditioners are all going to come on at the exact same time. And so what's happening is the amount of cold load is actually increased. This is not this. While the feed is de-energized, we have this hypothetical value called the cold load, which is the amount of load that will come on right at that instant. And then once that load does come on, over time, those homes will the air conditioners will bring the temperature back to the actual desired value, and so you'll get your diversity back again. And so after a certain period of time, you get back to the normal value. And so for restoration drills, modeling that cold load effect is very important. We've talked about the switch capacitors. For capacitors, very much the model is very much the same as what we talked about for planning. We have to model the balancing authority areas. We need the frequency bias. We need to know our tie lines. There's a thing called the ACE filtering, is that there are various coefficients that if there's a jump in the ACE, then it may be due to some bad data, so we'll actually smooth that out. And then, of course, all the different power system components have to be in one balancing authority area and only one, except for the lines which actually connect one to another. We have the governor turbine models. It's important to be able to model how the turbine and how the speed controller and the governor. We talked about the permanent droop, the 5% being the typical value. We need to model the inertia, and then depending on whether it's a hydro or a steam turbine, there's additional parameters to model the response of those types of turbines. So that gives you a very quick overview of the various types of models and the types of parameters that we're programming into them. And again, the idea is that under a wide range of conditions, we want to have all the mathematical models in there so that we can model the megawatt and megavar flows, the voltages, and the frequency, as well as and determine will the system go into a cascading outage. In the next segment, we will discuss the reliability coordinators and how their roles have evolved. This shows a map of all the reliability coordinators in the North American interconnection today. And a lot of the motivation for having this oversight came through the 1996 Western System blackout. And initially they were called security coordinators, and then they changed the name to reliability coordinators. And as a result of that blackout, NERC formed two working groups, the telecommunications working group, which looked at using the Intercontrol Center Protocol, ICCP, to bring data from the underlying transmission and balancing authorities up to the reliability coordinator level. Clearly, we can't run a reliability coordinator center unless we have the real-time data. And so that was the beauty of what's called ICCP, that the transmission operators would have the links in the terminal units and the substations. They were bringing that data in so they can monitor their system. So then let's pass a certain amount of that data on up to the reliability coordinator. And that working group specified the fact that each one of these transmission operators should have what was called an ICCP node. The data would be moved across a network called NERCnet. And this group started around about 1998 and continues to be in existence to keep that network running. Now, in parallel with that, we need to have the models. Each of these reliability coordinators needs to have a model of the entire system. So the Data Exchange Working Group was formed in the 1999 timeframe, and we were involved in what was called the Common Power System Model Forum, and through that forum, they said, let's require that every one of these transmission operators put their model in what's called a common information model format and pass that model on so it could be merged into a model of the entire region. Prior to this, the vendors had proprietary formats. We talked about PSSE, PSLF having an open format where you could download the user manual. The vendors preferred to have a proprietary format where literally if you were to read their documentation and use it to interpret the model out of their system, in some of the more severe ones, you would be under a threat of a lawsuit. And so those proprietary nature of those systems has been a bottleneck, but through NERC, the Common Information Model format, and it's called the XML, became a standard where at least you had a standard format that was supported by EPRI in the industry, and then there was a way, a lingua franca, for these utilities to take these models, which literally they had put many years of investment to building these, and get them moved across to other systems. And then fortunately with the Northeast blackout of 2003, this infrastructure was able to be, and what happened was the whole process and the responsibility of these reliability coordinators became a lot more visible, but at least we had the real-time data links and the model exchange formats in place to make sure that, that we had very good regional models built for each of the reliability coordinators. We talked about the impact of the Northeast blackout as well as the September 2011 Arizona Southern Cal blackout, and that has continued to influence the direction of the industry. Now, I think we have 8 out of the reliability coordinators are actually running central markets. When they run a central market, there's an extreme amount of funding available to run these applications, and so that becomes a natural function to run the reliability in addition to the central market. In the other cases, with WEC, Saskatchewan, TVA, Southern Company, Florida, Virginia, those are being run as sometimes as adjuncts to a major control center in the area. In the case of WEC, they have funded their own reliability coordinator function. In the case of the Southeast, the reliability coordinator function has been delegated to a large transmission operator. And so in that case, we see Southern Company taking it on here. Florida Power and Light takes it on for Florida. I think Duke Power takes it on for Virginia, and TVA take it on for their region. The WEC Reliability Coordinator started out where they were delegating, prior to 2009, they were delegating their function to Bonneville, California ISO, and Western Area Power in Loveland. And they were actually using different vendor systems with different models, but covering a piece of the WEC system. And then with a very large initiative, they said, let's bring all those 3 centers into 2 centers and have one integrated function with one set of software for the entire system. So they built what was called a West Side model of the entire WEC region. They merged the models from BPA, California ISO, and WAPA with this SIM format. And again, we see the importance of this Common Information Model format being available to let them do that. And they said, let's have a system in Vancouver, Washington, and Loveland, Colorado. So there's just some great opportunities for jobs as reliability coordinators, and we're proud to have placed some vets in those jobs. And it's a tremendous career opportunity to be on the and have a position where you're actually monitoring an entire interconnection. The idea is that both centers provide a backup for each other, and both centers monitor the entire interconnection together, and then there's a video display in the control center so that they can communicate with the operator at the other center. And so again, all of these applications are online and running. They do have their own simulator from Alstom, and a number of the companies do that for restoration drills, in addition to using the power simulator for different regions. So the entire model for this is available, and one of our goals is to also provide that for our cloud-based simulations in the future. Now, in the Texas region with ERCOT, their nodal market went live in December 2010, and again, a common information model was the heart of that. What ERCOT did is they said, we won't require everything to come from a single vendor. We will have Siemens provide the network model maintenance system, and then that system will be used to drive the energy management system and simulator from Alstom, and then we will have ABB provide the market applications, and we'll have a company called Nexent provide the congestion revenue rights. So that was another case where the common information model was a key to putting all those different applications together and making that system work. Now, the actual standards clearly drive the industry, but then when we have an actual blackout occur, everyone gets involved from FERC to NERC, and we see directives coming out and those directives often, in many cases, the reliability standards have been in place, but they weren't being complied with, and it's a matter of clearly showing to the industry and directing them to say, look, these are the types of procedures you need to put in place to be compliant with the intent of those standards. So again, if you're working in the industry, it's really good. Whenever there's a major outage or a blackout, whether you're on the job somewhere or you're looking for jobs, to be really in touch with what's happening and how is that impacting the whole market situation. In this particular case, Jerry Coley, the president and CEO of NERC, in July 26, 2012, provided a number of directives in a letter to the WEC CEO and said, we need to have sufficient staff resources and tools and training. The reliability coordinator has to have situation awareness of the entire WEC bulk electric system, and they wanted to have separate governance. The regions have certain functions delegated them by NERC for compliance. They have compliance officers that do the audits. They wanted to have that NERC delegated function separated in governance from the actual functions of the reliability coordinator, the planning coordinator, and the future energy imbalance market. So we'll actually see additional staffing and separation of functions and governance for that. They have to identify and update the ROLs. We talked about the risks from the remedial action schemes, that if we had the case where, remember, the path, the 230 kV path from Song, San Onofre Nuclear Generator, down to San Diego, that path went above a certain limit, and then the lines opened because of the protective scheme, the remedial action scheme. And so as those schemes have proliferated, all the entities haven't been advised, and we haven't programmed those into the simulators, which we need to do so that the studies and the simulators will have those limits. And then they'll have reliability data for the next day, as well as real-time assessments for the neighbors and WEC-wide. And the transmission operators, even the small ones, shall have access to the situational awareness with real-time contingency analysis, and will include the lower than 100 kV facilities. As said, as far as data sharing, we've seen one of the effects of 9/11 was a concern by utilities to share their data against both cyber and physical attacks. But in this case, as directed by Jerry Coley, there has to be a culture of trust in reliability data sharing to overcome the barriers. And that's just not the real-time measurements, that's the models as well. Okay, you need both to be shared. And so all of the RCs, the transmission operators, the balancing authorities should have access to the reliability data to perform the next day and real-time assessments, including the neighboring systems, and in some cases they need the entire interconnection-wide data. And there should be universal non-disclosures to allow that to happen. And of course, As part of that, we've been very privileged to be able to have access to this data to perform simulation studies, and we have to continue to exercise a lot of diligence to make sure it does not get into the wrong hands. All right, so let's now look at the scope of the operating models. Due to the difficult nature of building those models and maintaining them, and what we call about the detailed putting in the network list with the from and the to nodes, transmission operators have had a limited view of their neighbors, and they have just typically modeled the high voltage system, 100 kV and above, simply because it's a laborious effort to build those models and maintain them. And so the network applications just work for the high level view in terms of the voltage, and they just work typically to going to your neighbor's system or one or two substations into your neighbor's systems. And this may be okay for running just contingency analysis where you're looking at the steady state impact. But clearly these types of models don't work for looking at system stability where you have an entire interconnection possibly going unstable. And we have the issue that a lot of your model down at the 35 kV level, down to the distribution breaker, is not modeled using these applications. But that's basically has been the approach in the past. What we found for restoration training and operator simulator training is that it's really important to go down to the feeder breaker wherever possible. That's the area where you're picking up load. I mean, you need to be picking up load in 1, 2, 3 megawatt levels. So you're actually closing in on certain feeder breakers to pick up that load and to stay within your 5% limit. You're not closing in a breaker at the 115 kV level and picking up, 50 megawatts of load. So you've got to go down to that level. And that's what takes a lot of time. You've got to allow in a restoration drill to be picking up the load at that level. And so our smaller transmission operators tend to ask us to model down to that level because if they didn't, we'd only be modeling maybe a third of their system. The larger transmission operators, sometimes we still only model down to the 115, and we actually let them change the load in a percentage, okay? So literally, instead of picking up 50 megawatts, we say, well, we're just going to bring on 5% of that. It's also important, and we've really promoted this idea, to model the complete interconnection. If you're running a simulation study and you lose a 1,000 megawatt unit in Arizona, we went through this in the balancing class. Literally, every generator in the Western interconnection slows down a little bit. Every governor in the Western interconnection responds to that and brings the frequency back to a stable value. So we believe, and we've promoted this, of providing, by using the planning information, we can build a model of the entire interconnection. We can reduce the complexity by omitting the smaller, lower voltage lines if needed, but all the generation, all the prime movers, and all the load is in there to model that overall governing response. Some of our customers, of course, and especially after the Fukushima, are modeling the power plant auxiliaries. It's very important to have all the emergency diesels at your nuclear plant modeled and to make sure that they are providing the auxiliaries and, of course, get the power to those power plants within the specified limits if there should be a blackout. There's important we can do that for hydro plants as well as thermal steam plants. In these cases, we're updating those simulations every 1 to 2 seconds, and we're trying to give the most realistic view to the system operators during that restoration drill and simulation. And again, it would not be acceptable to our customers to just chop off all the lower voltage substations because that's in their area of responsibility. They have to monitor the substations at the lower voltages. That's an integral part of their job, and so modeling down to the lower voltage subdistribution circuits is a very natural part of these simulation exercises. And so we're trying to model the response of SCADA at stations of all levels at the SCADA rates. So we have to have this underlying topological model for restoration. There's an interesting scenario. This was built with Mark Sickles on the Alaskan system. Basically, on the Alaskan system, there's a couple of cables from Point McKenzie to Point Woronzof going underneath the Cook Inlet. 2 parallel cables at 138 kV. We have a whole scenario that we have a bus tiebreaker at the 15 kV level at the postmark station. And again, this is 15 kV. This would normally not be used in the models provided for the real-time network applications. But we can see in this scenario how it's really critical to model that. We have a case where the operator is requested to re-energize this cable by closing this breaker, and he's not fully aware of the impact of that breaker being closed at that substation. So what happens is, when he or she closes the breaker, and if this breaker is closed, we see real excess voltages. We see voltages going to 130%, so high that we could be damaging insulators, transformer windings. And why is that? That's because basically we had a backfeed. We energized this cable here, and then that energizes this bus here, which energizes this bus, which then energizes this entire cable here. So we had double the charging that the operator would have expected. So that shows the importance of modeling down to the lower voltage. When it comes to operator training, that's a really valuable scenario to teach. In fact, the circ operators have loved this scenario, and we're teaching that, and that rail belt model that was built on the Alaskan system has been shared throughout the country, and we're providing some very valuable learning lessons. But again, this is the issue of situational awareness. And we go over this over and again. You've got to have the big picture view, but you've got to zoom in and understand the detail. That one little, quote, insignificant breaker at a 15 kV level can cause a major amount of damage to equipment. So that's why we keep encouraging our customers to keep modeling down to lower and lower levels of detail. Clearly, we can't go all the way down to the customer homes on the feeder, but right now the feeder breaker is a very manageable point to take the level of modeling. We can show the importance of switching by going down to this case. It's a 34.5 kV network. We have a very severe type of fault is to have a bus fault with a stuck breaker. So we've got a fault on this bus here. Because the breaker is stuck, literally we clear out the entire substation. So if an operator should see this, the initial reaction, well, my RTU's gone bad, but in real life, this is a very common, very severe type of fault, where the fault is on one bus, the breaker is closed, so the other bus is also cleared as well. And then, of course, there's a whole procedure to rack out the faulted breaker and start restoring everything to service. But again, this shows the benefit of modeling down to the lower voltage levels for training purposes. So let's wrap up with the pros and cons of operating models. In the past, they were in proprietary formats, and the vendors typically didn't encourage a whole group of neighbors to work together. We haven't seen the models for dynamics like transient stability included in the scope, but that is changing. EPRI is working with all the vendors and utilities to add that to the common information model. Because the EMS budgets are large, there's typically other factors besides compatibility of neighbors that affect their buying decisions. And for different reasons, mainly the difficulty of maintaining these models The EMS buyers haven't required detailed models of the external systems, but clearly the impact of the most recent outage is encouraging people to look at the bigger picture view. So now let's look at the advantages of operating models. They're very familiar to system operators. From the operator point of view, he or she is seeing results come up on the SCADA one-line diagrams, just replacing in study mode the real-time measurements. They interact with those models by opening and closing breakers on a study version versus controlling a breaker in the real system. They can be updated to model the real-time conditions. The real-time data is coming in, it's being processed through the topology processor, the state estimator is finding the bad data, and so we can replicate the real-time conditions. And of course we have the breaker and switch configurations. Not the hypothetical single bus, single breaker with artificial names of breakers, but we're actually they're controlling and monitoring their breakers and their configurations with the names they're familiar with. We have the dependencies and line energization. If we come in on this line, we close the tie breaker here, the middle breaker, then we'll energize this line, and then we close this one to heat up the bus, and then we connect the other line that we want to go out through on a path. That dependency is there. We have generated capability curves, and we have accurate discrete tap configuration. So the models are much more accurate and they're real time. Some of the limits of operating models, we have them available now for the WEC interconnection, the Texas interconnection. There's still work to put them together to be available for the entire Eastern interconnection. They do require more sophisticated data management. It has been a more complex process to make model changes, and the vendor formats have not been published. And as a result of 9/11, it has been somewhat more difficult to get these models, but they can be available under non-disclosure agreements for consultants if they have a legitimate reason. We have to be more careful, whereas the generic PowerCo system, which you all can access, can be available to all scholars from all different countries. These models have to be available to just people where there have been background checks on them. So the SimXML is a great standard. It provides an open format with no legal limitations. But again, many of the model building efforts we took for the reliability coordinators were a one-time event. The operating companies transferred their model up, they were put together, but we didn't see an ongoing system in place where the transmission operators would keep exporting SimXML models and that they would be widely available. And the missing piece of the puzzle is that standard formats to exchange the diagrams are still not widely used. IEC has come up with a standard exchange for putting the coordinates out for the diagram. So clearly, if as a third-party vendor, you can go to a reliability coordinator and transmission operator and say, give me some XML for your model as well as your diagrams, and you can get applications running literally with no work by the customer. That is really going to open up the market in the future. So to review, on this module, you should now be able to describe applications of operating models, how those operating models are required to support the IRO standards. You should be able to describe the evolution of operating models from the early days, from the original vendors, systems control and control data, and in the role of Arizona State, Professor Bose with the EPRI OTS. You should be able to describe the overall structure of operating models using the UML diagram, and then describe what are the key components for models, what are the key attributes. You should also be able to describe the evolution of the NERC reliability coordinators, also describe the pros and cons of operating models versus planning models. Thank you very much.